Talk. Talking.
Okay, how about that? Can we hear that? asked question 9, okay. Number 9. Do, 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 do. Okay, maybe I can zoom in. There we go. Alright, so we have these two cars that are going to move toward each other and eventually crash into one another. So there are really two ways to go about this. The first way, which is what I've illustrated here and what should be coming up on the screen currently, is using a position versus time graph. Because we have constant velocity, the position versus time graphs are fairly easy to graph here. Yeah, the 30-second delay is a little bit irritating. So the key points that you need to get are that car A begins down here at position 0, where car B begins out at position 12. Car A is moving to the right, which I've declared to be the positive direction, which is why the slope of the line here is positive. The slope on the position time graph is the velocity. And so I've drawn a line starting at 0, 0, and going up to 7 at 5 seconds. The math there is basically that because the velocity is 1.4, I tried to look for a time when it came out to a round number, which in this case was, if I multiply by 5 seconds, 1.4 meters by 5 seconds gives me the 7 meters that I was looking for, which makes the graph a little bit easier to plot instead of trying to go over 1, up 1.4, whatever that is, and over 1, up 1.4, that gets a bit burdensome. So I chose to go over far enough that I could go up a whole number. I did the same thing for car B. Car B began at 12 meters, moving at negative 2.2 meters per second. So again, I did the same trick. I didn't want to try to plot every 2.2 meters, so I simply went out until it came out to a whole number, which in this case, again, at 5 seconds, 2 times 5 gives you 10, so that came out to a whole number, which in this case is negative 11. So from 12 over 5 down negative 11, that gives me 2 points that I can connect. I will now pause for 30 seconds to let you catch up to me. I suppose I could just print one of these out and do it on screen. Yeah, so once we have the graph plotted, literally all we have to do is look at the place where it comes together. The position time graph tells you here's the position at any time. The time when they're both at the same position is when they crash. And that you can read off fairly clearly is 3 1/3 seconds. And if we run that across, that's 4 2/3. It's definitely more than 4 1/2, less than 4, or less than 5. And you can see below how I've worked out the equations. All these equations that I have down here are literally the equations of the two lines that I've drawn. the y value of a is the slope, 1.4 meters per second times the time, plus the y-intercept, which is 0. For b, the y value is negative 2.2, again because it's moving in the negative direction, times the time, plus 12, which was the starting position. So all I'm doing is writing out the equations of those lines, and then solving for their point of intersection. Really wish there weren't a 30-second delay. So that makes sense. Hey, look, somebody else is here too. Well, not watching, but looking at the Unit 2 test. Sure, we can go through the Unit 3 test. Zoom in a little bit. Oh, that isn't what I wanted. I want to zoom. Oh, I am zoomed in a little bit. Okay, so Unit 3 test. We start out with a position versus time graph. The couple of things you need to keep in mind for position time graphs are that the slope means velocity. There are two slopes of concern. The first is a secant line, which I've illustrated two of them. Here I've connected the point on curve B from 0 up to 2.5 seconds. Well, I guess it's a little strange, so I'm looking in the wrong place. I'm going to move this camera. Let's see how that is. And that's a little better. Okay. Okay, so I connected point 0 to point 2.5 to illustrate a secant line. The slope of this line, as I've written there, gives you the average velocity between those two times, between 0 and 2.5. I've done the same thing from 2.5 to 5 because we're going to need that later. So that's the first slope you need to be concerned with, the slope of a secant line. The second slope of interest is the slope of a tangent line. I've also drawn one of those right here. You'll notice if you look carefully, which I'm going to have to zoom in a little bit farther, and there we are. Okay, get this coffee cup out of the way. As you can see, this red line I've drawn here just kisses off of the B curve right there at 5 seconds. That's what it means to be a tangent line. You just touch the curve, and the slope of the line is equivalent to the slope of the curve at that point. And I've drawn this to show that at 5 seconds, if the slope of this line represents the speed of B, and the slope of this line represents the velocity of A, then A is clearly going faster than B. So I will give a pause to see how all that went. All that makes sense? Alright, so when it comes to the motion maps, sorry about the little scribble there. A, because it is a straight line, we know the slope never changes. The slope is the velocity, so the velocity doesn't change. This is why I didn't measure terribly carefully, but the spacing between the dots should remain fairly constant. The spacing between the dots represents the distance the object travels during that chunk of time. And the intention is that each dot represents the same amount of time. Where it is its position. So in 1 unit of time, the object moves that far. In the next unit of time, it moves the same distance. In the next unit of time, it moves the same distance. The spacing stays the same because the velocity stays the same. The arrows represent that same information. The length of the velocity vector tells you the speed and the direction of the object. They're pointing to the right because these velocities are positive. Each of them is the same length because the speed is not changing. For B is also moving to the right, which is why the velocity vectors point in that direction. However, the slope of B is steadily changing, and it's actually getting less and less and less, as we can see by looking at these two secant lines, and ultimately this tangent line. From 0 to 2.5, it was going at a diminishing speed, and then from 2.5, it was getting even slower. What that means is that over time, it will cover less distance per unit of time. So at the beginning, it was going faster than A. So from 0 to 1, it covered a lot more distance than A from 0 to 1. From 0 to 2, it was still going faster than A, but not as fast as it had been, so the distance between the dots is less. From 2 to 3, it's going slower, so the distance is getting smaller and smaller, and it's starting to go about the same speed as A by this point. Had I continued, which I didn't, these would have gotten even closer together, ultimately getting closer together than the distance between A, because, right around 2.5 seconds, B starts going slower than A. From 2 technology for the win. How's it going, Max? Okay. Yes, it is. I actually have a brand new one down here, but it's not charged yet. Let me try it and see if it works. I literally just oh. Okay, let me try this new mic. Test. How's that? Can you hear me now? Okay, I'm going to assume, so correct me. Oh, I didn't answer that question, did I? I'm just going to wait for a sound check.
Test, test, test. Yes, one of my children is supposed to go on. I will turn mic volume. Okay, how about now? Oh, on. Level. Okay, how about now? That better? Test, test. Okay, I should have cranked it up a little bit there. Okay, so we're good on. Okay with second delay equals to no fun. All right, moving along. So for B, we're going to describe how is object A? Weird. Mic is okay. It's good now. Perfect. Okay. Object A compared to object B. As we look at the motion map here, we can see the most obvious difference is that B is moving with constant acceleration, while A is moving with constant velocity. You can see this because A has a constant slope, where B's slope is diminishing over time. So if we want to know how A is different than B, that's it. A moves with constant velocity, B moves with a diminishing velocity. That's really the only difference. You could go into some particular details, such as B is traveling faster at the beginning and slower at the end. But really the long and short is that B is accelerating, A is not. Getting into these things. Displacement from 0 to 5 seconds. Displacement is the difference between where you started and where you ended. Both objects began at 0. Both objects ended at this position here. That is to say they both started and stopped at the same place, which is to say that from 0 to 5, they both traveled the exact same distance. This is not true, however, if we only look at from 0 to 2.5 seconds. They began at 0, but by 2.5 seconds, B's position, which is here, I wish I could write on the screen, but I don't have that software installed. I'll have to get that. B has made it up here to about where the end is located, where A, by 2.5 seconds, is only to about where the O is. So that difference in distance there is the difference in their displacements. B has gone significantly farther than A. From 2.5 to 5, it's just the opposite situation. A started out well behind B. However, by 5 seconds, A has caught up to B. So during this time, the same amount of time transpired, but A had to cover more distance to catch up with B. We can work the velocity from two different angles. Either we can simply refer back to the displacements, because average velocity is in its most simple, well, not in its most simple form, but average velocity can be thought of as simply displacement divided by time. So from 0 to 5 seconds, their displacement was equal, and their amount of time was most decidedly equal. So their average velocity was the exact same thing. The other way you can think about it is using slopes of secant lines. So if we go back up to the graph, if we were to draw a secant line for object B from 0 to A, from 0 to 5 seconds, what we would find is that that secant line is actually simply the line that represents the motion of A. That is to say that on average, the motion of these two objects was identical from 0 to 5 seconds. So there are two reasons why we can say that their average velocities were equal. Average velocity from 0 to 2.5, well, we can look here and say, well, B displaced farther in the same amount of time, so it was going faster. Or we can look up at our position versus time graph. We can draw a secant line, as I've done here, from 0 to 2.5 for B. Then we compare the slope of the line which represents A to the slope of the line which represents B during that time, and we find that B has a larger slope than A, which makes B have the larger average velocity. That's what that means. Instantaneous velocity is about the slope at a point, which is why I drew this tangent line up here on the graph. This is tangent line to B at 5 seconds. The slope of this tangent line is approximately equal to the slope of the curve at 5 seconds. By comparing the slope of this tangent line to the slope of the line which represents A, we see that A has a much higher slope than this tangent line, which means that at 5 seconds, A has the larger velocity. Let me know when you're happy with that or if you have any questions. I feel like I need an announcer. Coming to you live from Midlothian, Virginia. Sweet if I just have to get it. I have to convince the school to let you guys use Google Hangout, because then it could be live, like live, and you guys could talk instead of typing, which would be nice. Okay. Oh, and there's my little comment in the header, and hey, look, page 2, there it is. Okay. Page 2 is effectively the same thing as page 1, except we're looking at a different representation of the motion. Instead of looking at a position versus time graph, we're looking at a velocity versus time graph. So let's talk briefly about what this graph tells us in general so that we can then use those things below. Yes. I would actually like to start doing this with some frequency. Like I said, I'd like to get the Hangouts figured out so that we could have faster interaction. The 30-second delay is no kind of way to do this at all. It takes too long. Yeah, we'd have to have some kind of rule, and I mean, honestly, how many people are going to show up for that sort of thing? I mean, being very frank, it's going to be 4 or 5 people at a time. And we'd have to have some kind of rule there. Actually, I think if I host the Hangout, I can mute and unmute at will. But I'd have to mute everybody by default and call on people. Okay, so looking at the velocity time graph. That, okay, maybe I can't do that. Gotta think about my monitor setup too. Anyway, this is a velocity time graph. The y value gives you the instantaneous velocity, which I've notated here. So finding instantaneous velocity using a velocity time graph is really quite trivial. You simply look at the time you want and read off the y value. Average velocity can get a little stickier than that, but the idea is that you and literally just take an average. Say, okay, between here and here, on average, where were they? Well, in fact, they were 6. Between 0 and 2.5, the average was 6. Because this is a line, you can simply use the midpoint theorem, which is to say that you take the 2 endpoints of the segment you're interested in, average out the y values, that tells you the average in the center. So we can find average velocity as long as this is linear quite easily. The average velocity for B between 0 and 2.5 is 6. The average between 2.5 and 5 is 2. Oh, this is no trouble. I'm glad that you guys came out to check it out. There are a bunch of people in the Google Docs right now probably should be here who aren't. So I don't really know what to, oh, that's not the right thing. Yes, so their loss, your gain, right? I'm not seeing my list of, because I'm zoomed in so far on this screen, I can't even see it. No? I don't know. Anyway, this isn't the right test. Okay. Whoa. I'm lost. Unit 3, where are we? Full makes sense. Okay. Scrolling down. Okay, we're back. Sorry. Comments below. Okay, back again. So we covered average velocity, how you find that. You can also look at the fact that average velocity is displacement over time. And knowing that the area under the velocity time graph gives you displacement, you can calculate the displacement, calculate the time. Yes, I'm actually going to have to go and cook my family dinner pretty soon as well, so we'll have to roll through here. I will probably be able to come on later this evening, and maybe I'll do tomorrow as well, but that doesn't help you guys because I think we test tomorrow, right? Yes, now that I've figured out how I can do it, it'll be easier to make those decisions. It was my intention to have these announced ahead of time. It just didn't work out. All right, so quickly looking at the position time graph or the motion maps. A again has constant velocity, just like in the previous one. Constant velocity means you cover the same distance every time, so the spacing between the dots doesn't change. Arrows represent the velocity. The velocity is a constant positive 4. If all the arrows point in the positive direction, they're all the same length. For B, we again have this case where it starts out very fast and slows down over time, which is why the velocity vectors, they all point to the right because the velocities are all positive, but they start out long and get shorter and shorter and shorter and shorter. The spacing between the dots gets smaller and smaller as time goes on because the speed is smaller. To have a slow speed means you don't go very far in one unit of time. So each unit of time that passes, the distance the object moves gets smaller. The acceleration vectors, which are there, are all pointing to the left. This is because acceleration is the slope of the velocity time graph, and we see that the slope of this graph is a constant negative value. So the arrows point to the left, which is the negative direction. They're all the same length because the acceleration is constant. Oh, stretch. Okay, answering these questions. Instantaneous velocity at t equals 0 seconds. We're looking at a velocity time graph. The instantaneous velocity is the y value. At 0 seconds, b is going 8 meters per second, a is going 4 meters per second. B is going decidedly faster. At 2.5 seconds, again, we're looking at instantaneous velocity, so we're going to read off the y value from the velocity time graph. Both of them have a velocity of 4 meters per second, so they're equal. At 5 seconds, we're again simply comparing y values. B has a velocity of 0, A has again a velocity of 4. A has a greater velocity. 4 is greater than 0. There's your larger velocity. These average velocity questions. From 0 to 2.5. If we look at A and B from 0 to 2.5, B goes from 8 down to 4. A is simply 4 the entire time. So B, until the very last instant, was always going faster than A. So on average, it was definitely going faster than A. That's one way to come at this. The other way is to think about displacement. The one that is going faster on average will have displaced farther during the amount of time. We can compare the areas of these and see that B has this entire triangle that it doesn't share with A. The displacement of A is only this area down here, where the displacement of B is both this rectangle and the triangle. So from 0 to 2.5, B has displaced, this is actually 50% further than A, which means it was going on average faster. From 0 to 5, okay, so from 0 to 5, there are a couple of ways to look at it. We just look at the velocities. B goes from 8 down to 0 in a linear fashion. That means that its average can literally be found by simply saying 8 plus 0 divided by 2 to get 4 meters per second. Because this is a line, we can just take an average of the endpoints to get the average. A is always going 4, so which average is 4? Their average velocities are the same. The other way to think about it is to look at the displacements. From 0 to 5, the displacement of A is this entire rectangle. The displacement of B is this entire triangle. And on inspection, you'll find that this upper left triangle is identical to this lower right triangle. So if we were to pick this triangle up and stick it down there, find that both of them actually had a displacement equal to this large rectangle for A. So their displacements are the same between these two times. They covered the same distance in the same amount of time, so on average they were going the same speed. And we just answered these two questions. The area under the velocity time graph is the displacement. It has a larger area than A. It is the rectangle and the little triangle, where A is simply the lower rectangle. From 0 to 5, on inspection, you can see that those areas are actually the same, or you could actually go in and calculate them. A is simply a rectangle, so it's length times width. 5 times 4 is 20, so we have a displacement of 20 for A. B is a triangle, so that's 1/2 base times height. 1/2 of 8 is 4, so there's your 1/2 height times the base. 4 times 5 is 20. Both of them have a displacement of 20 during that 5 seconds. Okay, for the last question. Acceleration is the slope of the velocity time graph. The thing to remember for this, and the mistake that people always make, I'll even go so far as to say this is a trap that people fall into, is that we forget what the sign means. In math class, the sign actually tells you about the size of things. But in physics, that isn't what we mean. In physics, the sign is direction. If it has a positive value, it's pointing to the right, or whatever you've called positive. If it is a negative value, it's pointing the other way. So in this case, when we look at the slopes, yes, B has a negative slope, which is to say that the acceleration points to the left, as we've displayed here on the motion map. A, the slope is 0. There is no acceleration. So when we actually compare, instead of the numbers, but when we compare the length of the acceleration vector, the thing we use to represent the acceleration, find that, look, A doesn't have an acceleration. There's no length at all. B, it's pointing to the left, but there is length. So that's why we have to conclude B has a larger acceleration, mostly because A isn't accelerating. Any acceleration is bigger than no acceleration. Yes, you're in very good company, having fallen for it. And that's sort of why this is here, is to remind us of that idea. We have to always keep in mind, what does the sign tell you? The answer is direction. The sign tells you direction. All right. Uh-oh, did we lose Max? Bye, Max. Yep, lost Max. a do, and a do. Go. All right, I'm going to go into these graphs, or I need to see what was going on there. The main idea is that to get the velocity graph, you look at the slope of the position time graph. Here, the slope goes from very steep and negative. It gets less and less and less until it is actually 0. Then the slope goes positive and gets bigger and bigger. The acceleration is the slope of the velocity time graph. The slope here is constant and positive. So the acceleration is constant and positive. Same idea for these guys. Whoa, we have lots of people now. Hello, viewers. Who's here? Everybody say hello so we can see who we're talking to. Well, I'm told there are 4 people here, but that's okay. Don't want to be all antisocial and stuff. Alright, so we okay with these graphs, or would you like more detail on? I am watching on my phone from the other account. I'm unable to make comments through my phone, but I can listen in. Oh, you guys can read. Excellent. Okay. Yes, I'm sure it will be a blockbuster one day. It might show up on my YouTube account. I doubt it, though. And I just don't think you're going to want to sit there and watch that whole thing. Okay, so I'm going to move on to this one. Actually, I'm going to go grab a drink of water, and then I will continue with this. I will be right back. Sorry, we're back. Yeah, I think that it will save to my hard drive, and I would be able to upload it later. I have to convince YouTube to upload long videos, though. All right, good. So let's look at number 4 here. Teacher's car can go from rest to 25 meters per second in 10 seconds. Car's velocity changes at a uniform rate. Draw a qualitative motion map to represent the motion of the car during 10 seconds. All right, so I've declared that to the right is the positive direction. Begin at rest. That means that the initial velocity is 0, which is why I've elected to draw this first dot here with no velocity vector. And also why at the second time, there is no motion. We have the same position for the first two dots. Here we get a small velocity vector, and over time, the distance between the dots gets farther because we're going faster. Velocity arrows get longer and longer because we are increasing in speed. The acceleration here is constant. This is what it says. The car's velocity changes at a uniform rate. That is to say, the acceleration is constant. So each of our acceleration vectors points to the right. We know it's to the right because our velocity is increasing. As we look at our velocity time graph here, velocity goes from 0 to 25. The slope is positive. That means our acceleration is positive. We also looked at, in class, we built that chart of the direction of velocity versus the direction of acceleration based on whether you are speeding up or slowing down. This is a case where the velocity is positive, we're speeding up, so they have to be in the same direction. Our velocity time graph. We're told it starts at 0, it gets to 25 in 10 seconds. So at 0 seconds, we're going 0. At 10 seconds, we're going 25 meters per second. Connect those 2 points with a line. The slope is acceleration. Area gives us displacement. The y value gives us instantaneous velocity. The acceleration of the car. Well, acceleration is the slope. So we look at our graph, we pick off 2 points. I've chosen to use the first and the last point because I know that those two are exactly right. They were given. Acceleration is the slope. Slope is y2 minus y1 over x1 minus x1. This is a common error. People like to do this upside down. Don't do it upside down. At 10 seconds, we're going 25 meters per second. At 0 seconds, we're going 0 meters per second. So our slope is 25 minus 0 over 10 minus 0. Calculating the slope. That reduces to 2.5 meters per second, which again, acceleration is the slope of the velocity versus time graph. I like this headset because I can drink without moving the boom. All right, determine how far, I can actually read the words that are there. How far does the car travel during these 10 seconds? Okay. Translation, how far does it travel? That means find the displacement. Displacement is equal to the area on a velocity time graph. This is a triangle. The area of a triangle is 1/2 base times height. Base we're interested in is the time from here, there. That's 10 seconds. The height of the triangle, from 0 to 25 meters per second. That's a height of 25 meters per second. Multiply through, you get 5 times 25, which is 125 meters. Again, the key here, displacement is the area between the velocity time graph and the t-axis. E, how fast is the car going 3 seconds after it starts? This is asking us to find the instantaneous velocity. That is, what is the y value at 3 seconds? The easiest way to get this is to simply go to the equation. This thing is a line. Y equals mx plus b. I know that the y value is what I'm looking for. That gives me the instantaneous velocity. I know that the slope is the acceleration, which we've calculated to be 2.5. X is the time I'm interested in, which in this case is 3 seconds, somewhere in here. And the y-intercept is the initial velocity, which was 0. So I've recorded that into the equation. The velocity at any time, the slope 2.5 times the time. At 3 seconds, we fill in the 3 seconds, find that that velocity is 7.5 meters per second. Irritating that there's all these blank pages. Okay, this guy. Still doing all right? Okay. Here we are given a sort of limited motion map, and we are asked to do some things with it. The first thing is to plot a position versus time graph, which is good because, well, that's basically all that we're told directly here. We can read off the positions from this thing. So, first thing, plot the points. The first dot is always t0, and it's stated right there that this is t0. 0, 0, there's the first point. At 1 second, it is, something small. So I've plotted it down here at something small. It's about 1, and in actuality, it is 1. At 2 seconds, it's just a little bit shy of 5, which we'll call 4. So we plotted that. At 3 seconds, a little shy of 10, which we've called 9, so on and so forth. We plotted the points. Hopefully we're good with plotting points. Drawing some lines, we'll get to those in a second. How we're going to find instantaneous velocity is the question. And there it is, 2 ways. We're looking at a position time graph, there are 2 ways to find it. Either we find the slope of a tangent line, which I've drawn here, this longer red line is the tangent line at 5 seconds, or we find the slope of a secant line centered at 5 seconds, which is what I've done here from 3 to 7. And you'll notice as you look here, the slope of these 2 lines is almost identical, and that's the idea. They're going to be the same thing as long as this is a parabola, which it is. Now we're actually going to do it. So I've selected to do the secant line procedure because I don't want to go through the bother of finding points on this thing. So I simply used the 2 points that I connected with my secant line, which were 749 and 39, again being careful to do our slope the right way around, which reduces to 10 meters per second. You can see that on this tangent line as well. If we go over 1, go up 10. This is 25, 30, 35. Over 1, up 10. 1, up 10. Calculate the average acceleration. Okay, acceleration is the slope of the velocity time graph. So we need a velocity time graph, which is why I drew one over here. We just calculated the velocity at 5 seconds, so we can plot that. At 5 seconds, the velocity is 10. Looking at this case, we can also say, look, the velocity at 0 seconds is 0. The slope of this thing, if we work it backwards, is getting smaller and smaller and smaller, and at 0 it disappears altogether. So we're going to use that as our other point. 0, 0. The slope here, we go over 5, up 10. That's a slope of 2. The other option, if you didn't see that this thing has a slope of 0 at the beginning, you could do the same trick we did here at 5 seconds at some other place. You could simply connect, well, we need a point in here. Connect 0 to 2, find the slope, put that on your velocity time graph, and find the slope between those 2 points. Key to this is remembering how to get acceleration. We need a velocity versus time graph. So go draw one. Boy, very tired. Okay. The bullet train. So here are the big questions, right? Bullet train slows from 50 meters per second, which I've labeled to identify this is the initial velocity. It's the velocity we were told, this is the starting. To a speed of 40 meters per second, that's the other velocity at the end, in 500 meters. Paying attention to the units is very important. A lot of people want to use this as their time. This is not the time. 500 meters, that is most decidedly a distance. That's the displacement. Slowed down from 50 to 40 meters per second. It took it 500 meters to do that. How much time? Don't know. We are asked to find the acceleration. Immediately we say to ourselves, I know what acceleration is. It's the slope of the velocity time graph. Well, I better draw a velocity time graph. I did sketch a little picture here to organize my information. My train at t0, position 0, velocity, all of that. Yes, these are the hard ones. This is why this part of the test got its own whole day, right? Okay, so our velocity time graph looks like this. We started at 50, we ended at 40, don't know how long it took. So we simply give it a name. We said that when it's going 40 meters per second, the time is TF, the final time. We don't know what it is. We need to find the slope. Well, we don't have enough information to find the slope because we don't know the coordinates of this point. We only know the coordinates of this one, which are 0, 50. We don't know the coordinates here, so we have to figure out a way to go and get that time. There's another thing we know. Apart from the equation of this line, which I used here to find our acceleration, we know that the area under a velocity time graph gives us the displacement. We were told the displacement. The area under here is the displacement, which is 500 meters. Looking at this shape, this is a compound shape. It's a rectangle with a triangle stuck on top. So the area of the whole thing is the area of those two shapes stuck together. 1/2 base times height is your triangle. Length times width is the area of your rectangle. A couple of things that can get you hung up here. The base, we don't know, but we've named it. So don't leave it a B. We know that it is, we're calling it TF. It is the time that we're looking for. So I've changed the base to TF. I've changed the length of the rectangle to TF. Making substitutions here. The height, we don't want the height of the whole shape. We only want the height of the triangle. The triangle is simply this top shape, so it goes from 40 to 50. That's only a height of 10. The width is the width of the rectangle, which is from 0 to 40, which is 40. Bit of simplification. This becomes 5TF plus 40TF, which gives you 45TF. We know that the whole displacement has to be equal to 500. 500 over 45 gives us 11.1 seconds. Taking that, putting it into the equation of our line. The y value is the velocity, the slope is the acceleration, which is what we're looking for. The x value is the time. The y-intercept is the initial velocity. Filling in what we know that at TF, which is 11.1, the velocity is 40. So we can fill that in. 40 is whatever the acceleration is, times the time, 11.1 seconds, plus the initial velocity of 50. Subtract the 50 over there, gives you -10. -10 divided by 11.1 gives you an acceleration of -0.9 meters per second squared, which is to say the acceleration is in the negative direction with a size of 0.9 meters per second. Which is to say, in this case, the train slows down by 0.9 meters per second each second. These types of questions always come down to the same two things. You're going to write the equation for the line, and you'll know some of the information, not all of it. You're going to write an equation for the area, which is the displacement. You're going to know some of the information, not all of it, but between the two, you will have enough information to answer the question. You'll see as we go into this next one, it's the same thing. On which part? When you approach these, literally just do this. Just write down, I drew this velocity time graph, I'm going to write the equation of the line. I'm going to substitute in everything I know. I know that the area is the displacement, so I'm going to write an equation for the area. I'm going to substitute in everything I know. Then it becomes a math problem. You have two equations with some variables you don't know. Solve them together. 40 becomes the base. Okay. I'm pointing at the wrong place on my screen. I wish I could draw here. So the rectangle runs, we partition off. Actually, 40 doesn't become the base. 40 is the width of the rectangle. If we're calling this the length, 40 is the width of the rectangle. Sorry, I'll be right back. Sorry, I'm all of a sudden not feeling terribly well. So I am back, and I'm just gonna sort of pile through this because I've all of a sudden started not feeling very well. Okay, so we're dropping a rock. There's a code word here. When you drop something, initial velocity is 0. So that's a code word. Whenever you see dropped, initial velocity is 0. Hits the water 3.2 seconds later, that's your time. We're asked to find how high is the bridge. The height of the bridge, that's going to be the displacement of the rock. It starts at the top, it goes down until it 3.2 seconds later. I've organized our information here. Initial position, initial velocity, initial time, all zeros in this case. Down is negative. Our acceleration, an object falling on Earth, always has an acceleration of 9.8 meters per second squared down. Final position, we don't know. This is pretty much what we're looking for. How tall is the bridge? How far was it from here to there? Final velocity, we don't know. The time, however, we do know is 3.2 seconds. So we draw on our velocity time graph. I filled this in later. Initially, we don't know what this is, but we do know that at 3.2 seconds, it is going some velocity, and we do know that the slope is negative 9.8. So I've gone to the equation of this line, y equals mx plus b. Y value is the instantaneous velocity, slope is negative 9.8, x value is our time, the y-intercept is 0. Filling in what we know that at time 3.2, velocity is VF. It's two things together. We know the slope, we know the time, the y-intercept is 0, so VF is negative 6 meters per second. Now we know that. Well, we know that the displacement is the area. Triangle, 1/2 base times height. The base is the time, the height is velocity at that time. We know both of those things. Time is 3.2, the velocity is 31.36. You multiply those, you get negative 50.176 meters. But we want to know the height of the bridge. No bridge has a negative height. So we change that over to a positive value. The displacement was down, which we've called negative, but the height of the bridge is positive, 50.2 meters. And on the last one, go about it the exact same way. We're told the acceleration starts from rest. There's your code word. The initial velocity is 0 again, from rest. How long will it take him to travel 16 meters? That is his final position, which in this case is the same. Why wouldn't the equation just end at, because it is not 31.36 meters, it's 31.36 meters per second. This is a velocity. That tells us how fast it's going, not how tall the bridge is. That makes sense? That's a ton of people stopped at 31.36, but that's not equal to displacement, that's equal to the velocity. Right, so we're going to play the same game down here. We know the initial velocity was 0. We know the slope was 2. So we've drawn that. I don't know the time or the final velocity, but I do know that I can write the equation of this line. Y is mx plus b. The velocity is vf. The slope is 2. X value is tf. The y-intercept is 0. So the velocity anywhere is 2 times the time. I want to know at this time what is the velocity. So I filled in the velocity vf is twice the time tf. We just don't know what either one of them are. Also know that the displacement is the area underneath this thing. We know its displacement at 16 meters. So 16 meters is 1/2 base times the height. Base is tf. We don't know what that is. The height is vf. We don't know what that is, but we call them variables. When we look up here, we see, well, we don't know exactly what VF is, but we do know that it's twice TF, so we can substitute that in. And when we do that, we eliminate a variable altogether, leaving us TF and TF. This reduces down to TF squared. Take the square root of both sides, and you find that TF is equal to 4 seconds, which is exactly what we're looking for. So each one of these really reduces down to the same thing. You write out the equation for the displacement, you write out the equation of the line, substitute in what you know, and the remainder falls out. It becomes an algebra problem that you can solve.